Also, don't forget if you need to see the screen from where you're at, you should be logging in to Google Meet. All right, so time is up. You should be wrapping up on the bell work after Rachel. You should be wrapping up on the bell work at this time. Your headphones should be off because you should be paying attention now to the lesson, and we're going to go ahead and get started. Remember, this is the only lesson this week. This lesson feeds directly into the lab we have next Monday. The next lesson in this unit, we're not going to actually do, I believe, until next week, Thursday. We've got a weird schedule coming up. Next week, Wednesday, is actually a teacher planning day. There's a day off next Wednesday at the end of the quarter. With that being said, a couple of things grade-wise. First off, I had already said, but I'm going to say it again, that your game points, I'm going to update those for next class period. So I'll give you that update right at the beginning of bell work before you go to testing. Yeah. All right, so once again, we're continuing with content. Our first lesson is this week. We're not going to have another lesson until next week, Thursday. So make sure you're paying careful attention. Everything we do today, the exercises and practice, we're going to do over the next several class periods. And then we'll move on to lesson 2. This is another math-intensive unit. Just to give you the heads up, this is technically the quantitative analysis part 2. But in this unit, we're going to specifically be looking at a couple of different ideas. The first one is we're going to be looking at the math of solutions. And the second is we're going to be looking at the math of acids and bases. So things like calculating pH. And in this lesson today, we're going to learn how to calculate concentrations, which means how much do we have in a given solution of some specific substance. And so make sure, once again, you have a calculator. that you're paying careful attention. I am recording in this class today. I'll be posting the notes after school for all the class periods for this lesson. And so let's go ahead and get started. There will be a couple of questions in your notes that will say your turn. And those are the ones I'll be looking for stamps when we get to those. Make sure as we go through each lesson, the rest of the year, by the way, there's only, I counted them out, we only have about 9 lessons left till the end of the year. Believe it or not, this unit isn't extraordinarily long. It's only got like 4 or 5 lessons in it, and the last unit only also has like 4 or 5 lessons in it. So we're close to being done with the year. 2 final units, technically you can think of today, even though quarter 4 starts next week, we're starting quarter 4 content today.
Good morning. Please pardon this interruption. At this time, please release the chess team and Tyrone to test in 249. Again, the chess team and Tyrone. It should be 7 students in total. 249. Thank you.
Good luck. What day are you coming back technically? Tuesday next week?
Monday night.
Monday night. Good luck today and good luck on that tournament. They're going to nationals, right? Do you know how to play chess? You break your leg?
Oh. Is it gold break the leg? I'm breaking
Have
the
a good
other
day. Take care.
Good luck.
All right, so let's go ahead and continue. Once again, we are starting Unit 7. Unit 7 isn't extraordinarily long. However, there are several labs which will space it out a bit. You can expect to have no quiz in this unit, and technically no quizzes this entire quarter 4. You're only going to have 2 exams, one for Unit 7 and one for Unit 8. In terms of time gets kind of squished as we get to testing season, so that's why you'll have 1 exam for Unit 7, which is only 4 or 5 lessons, 1 exam for Unit 8, which is also 4 or 5 lessons, and then we'll be done with the content for the year. Now that seems like, oh, it's only going to be a few weeks, but no, it isn't, because as like for Thursday, we're not technically going to have class on Thursday because of testing. That's going to happen several times throughout the quarter 4. So pay careful attention to what the schedule says, like I had told you, and if I need to, I'll update you on Google Classroom with whatever's coming up if there are any changes that take place. Daniela? The other thing is Google Classroom for now, we're still in. I'm going to stay in Google Classroom through the end of the school year unless I get kicked out. So expect to stay in Google Classroom until we're not allowed to use Google Classroom. And right now it's still allowing us in at the school, so I'm going to continue to use it. I do have Schoology as a backup, but I'll only switch over if need be. Otherwise, I'll be switching over for next school year. So just heads up, we're still using Google Classroom. It is the easiest integration, and changing everything over in 4th quarter is kind of difficult. So let's go ahead and get started. First thing, well, we actually already talked about solutions this year. We did it back in Unit 4. In Unit 4, we learned about mixtures, and we did an introduction to chemical reactions. So the first several slides you're going to see are a review of what we did back in December, which, by the way, was like 4 months ago. And I thought about that yesterday. I was like, time just flew like crazy. Because it didn't seem like that long ago we were covering this, but it was apparently 4 months ago, back in December. So a couple of things you need to remember to bring back to memory, because we're going to be using the terminology throughout the unit. What is a solute? What is a solvent? And what is a solution? A solute is whatever you're dissolving. A solvent is whatever does the dissolving. And then a solution is whatever you're putting together, right? So in its simplest term, a solute is what is getting dissolved, typically some kind of compound, could be covalent or ionic. A solvent is what is doing the dissolving. Which, do you remember, at least for the purposes of this class, what's pretty much almost always the solvent? Water, right? If water's mentioned, it's water. And then a solution is your combination of however many solutes you have and the solvent that they're being dissolved into to form what we call a homogeneous mixture. What mixture meant? So it's a same composition throughout or thoroughly mixed. And another way of describing it is it exists as one phase. You can't take out the components, it all looks the same. It exists as one phase. So just real quick reminder, I have here, and I'll be referencing some of the labs we've done in the past, and I told you there's a lot of labs in this unit, which is going to extend it out of it, which is good though, because you get more practice, more fun activities. But we did a lab where we dissolved different compounds into water. I just took sugar, dissolved it in water. What was the solute here? This is sugar, and then this was my water. So just whatever's getting dissolved, we call that by definition the solute. And then whatever's doing the dissolving, that's the solvent. For the purposes of this class, we work with aqueous solutions. The solvent's going to be water. So you don't have to get confused with it. And then a solution is everything mixed together. And so what you're going to be doing on Monday's lab is you are going to be creating a solution of a specific concentration, and then you're going to be diluting it. You're going to be learning some new techniques and skills, like laboratory techniques and skills that will help you throughout future labs. There'll be a later lab this month that is called an acid-base titration, which you'll need the skills you learn on Monday in order to do that lab. So I'd like to build it up one step at a time. There's a formula here that I mentioned before, and it's just the idea that if you want to find out how much solution you have, all you have to do is add your solute and your solvent together. The one thing that I wanted to bring up is that your units have to match, and you'll see that in a question very shortly. Right here. So this is the first type of question you could be asked, and yes, I could ask you a question like this on your next unit test, and I would expect and hope that you could get this correct. Technically, because it's reading comprehension. Determine what is the solute, what is the solvent, with the given information, and calculate the total mass of solution. So it tells you 10 grams of NaCl are dissolved in 100 grams of water. Identify the solute, identify the solvent, and calculate the total mass of solution. So what do we mean by identify?
Why do you define which one is which?
What is the substance, right? We're looking for what specifically is the substance that's the solute. What specifically is the substance that's the solvent? And then we'll do the calculation of the total mass of the solution. So what is the solute?
Solute is NaCl.
And that's how we would answer. We would just say salt. Salt is the solute. And then the solvent is?
Water.
Now, I do want to bring that up. Did they say we had to write the chemical formula?
No.
So we could either reference it by formula or by name. The same is true for Cambridge, actually, in the AICE course. If they just ask you to identify something and they don't say how they want you to identify it, you can actually call H2O, you can just call it water. And they're fine with the common name. You don't have to call it dihydrogen monoxide. It's cool, water's fine. But that's the solute, that's the solvent, and then total mass. How do we get the total mass of solution?
Solute is solvent.
Okay, so what's that gonna look like?
100 g of water.
So it'd be 10 grams, and that's the NaCl, plus 100 grams water. Do those units match? Why not? They're both grams. What do I mean by the units have to match? They are both grams. They match. So that means we literally just add 10 and 100 together, and we get, guess what? We get 110 grams. 110 grams of light. And the solution is?
Water.
I look at it. NaCl, AQ. I have to delete the slide to get back in the meeting. Let me check. Hold on. There's somebody out right now. So the answer here would just be 110 grams, and NaCl dissolved in water, or NaCl(AQ) is the way that we've referenced that in the past, salt in water. I'm going to delete this so I can get back in the meeting. But the final answer was 110 grams, and that was NaCl. So the only way that this could be more complicated is, for example, if I gave you one unit in grams and another one in milligrams, and then you would have to convert the units to make them to match. And you're going to see that later on with other examples today where the units don't match, and you're going to have to make them match before you can do the math you have to do. So conversion factors are not leaving. You still have to know how to convert. All right, we're moving on. This is also review from earlier in the year, back in Unit 4. We defined homogeneous mixtures back then. And we said that a homogeneous mixture, we also call this a solution. And for the rest of the class, we're not going to really talk about homogeneous mixtures. We're just going to reference everything as a solution. Yes. You're second in line right now. Homogeneous mixtures, it's interesting to note that could be liquid mixtures or gas mixtures or even solid mixtures. And so I wanted to bring up an example of each. So a liquid solution, a gas solution, and a solid solution. And let's think if we could think of at least one example of each. So what would be an example of a solution that's in the liquid phase? Not just H2O. Salt water or sugar water, something like that, right? Something where water is the solvent and you've got something else being dissolved into water. That's an example of what we're going to mainly work with in our class. So, salt water. By the way, if you're studying AICE Marine Science next year, that's your choice that you chose, you're going to be working with salt water all the time because most of that class, or a lot of that class, deals with the ocean. And the ocean is water with salt. So you'll be doing calculations. You will be doing calculations. You'll be looking at graphs with salt water. That will be what a lot of that course is about. So a lot of students, if you don't like chemistry, you have to know some though, because no matter what class you're going to move on to, it involves chemistry actually. And Mr. Dime will tell you that. Ms. Purcell will tell you that when you get to those courses. He's like, didn't you learn that in chemistry? Like, I didn't. But a lot of this material runs through. This is a foundation class. That's why it's so important that you learn these ideas and concepts, because it helps you with your future courses, whatever that future science course may be. So salt water, liquid solution. What about a gas solution? Can anybody think of a gas solution that exists? There's a very, very famous one. Oxygen's not a solution though, it's an element. That's it. Solution, remember, is a mixture, right? Everything's in the same phase. Hydrogen is an element, right? Air. One phase, mixture of gases that exist. Oxygen, nitrogen, all the things you were shouting out. Carbon dioxide. A gas solution is air. One of the classes where you study the air is environmental management. So if you're taking environmental management next year, you'll be studying air, you'll be studying air quality, you'll be studying air pollution, and what are the pollutants, what are like the greenhouse gases. But a gas solution is air. So gas solutions exist. It's one phase. It's got multiple things in there, and we can't pick out. I can't be like, oh, look, there's the oxygen right there. You can't see it to pick it out. Finally, solid solution. This is the one that I always would think that you might get stumped on, but yesterday Students did not. Can you think of an example of a solid solution? Meaning one phase, but there's multiple substances contributing to that one phase. That's still an element. It's an allotrope, but it's an element. Has to be multiple different substances, right? But they form one phase. Ice is water. Yeah. That's an example. Yeah. Any alloy, so steel or brass or bronze, is a mixture, but it all exists as one phase. Those are all considered solid solutions. So alloys like steel. We actually made one earlier this year. We made a alloy. We made brass. It was what you saw as the gold pennies. We made brass. We made a solid solution actually, which was a mixture of zinc and copper, and it made that pretty color that you got. So yeah, you can have all three phases solution, but for the purposes of our course, we don't really talk about these two very much. We're going to spend all of our time talking about water, and pretty much this whole entire unit, solutions, acids, and bases, it's all going to be about water. But I just wanted to expand your focus a little bit just to note that there are other solutions that exist that can be met. All right, we're going to go ahead and continue. The next thing, and I believe that this I did not cover in the part one of solutions that I did, so I'm covering it now. The next thing you need to know is something called an electrolyte, which you may have heard this term before, especially in marketing. Yesterday, students were able to give me several examples. Can you think of any time you've heard of electrolytes in the past? Gatorade, right? That's their whole marketing strategy. And what were the purposes of it? Why does Gatorade advertise electrolytes? These electrolytes work out and it replenishes electrolytes. What do you mean by that? What is it actually replenishing? Like, what is the actual minerals? Yes. I'm sorry? It's not energy, actually. The minerals do not provide energy themselves because they don't have calories. What would it be? What's an electrolyte? And so the formal definition, where it has to do with electrons, right? The beginning is electrons. And so the actual definition for an electrolyte is a compound that conducts electricity when it's placed in water. So the reason why they add electrolytes into Gatorade, and there's other substances like Pedialyte that also do this, is to replenish your ions that you need for things like your sodium, potassium pump in your heart. And so when you exercise, you lose some electrolytes and have to regain them back to maintain the balance. And so compounds that conduct electricity when placed in water. Have we done that in the past, actually?
Yeah.
We did, in a lab. We did a lab where we took different compounds, we put electrodes in them, if you were here that day, and we saw that in the solid phase, they did not conduct electricity. Some of you got mad. You're like, every single one of these doesn't do anything. And then I had you afterwards put them in water, and you should have noticed back then, oh, all of a specific type of compound always conducted electricity when it was placed in water. Do you remember which one it was? There are two types of compounds, are covalent and ionic. Which one do you think conducts electricity? Ionic, because there's charges. And so compounds that conduct electricity when placed in water are ionic compounds, because ionic compounds by definition have charges. And so when they separate into water, and I'm just going to write here metal with a plus charge, non-metal with a minus charge. When they separate in water, you've got ions, and ions have charges. And what is electricity? Really a physics question, but in case you haven't taken physical science, what's electricity?
Energy.
It provides energy, sure. Electrical energy, but what is electricity? What is current? What has to happen for there to be electricity?
Fire.
It does have something to do with electrons. Current, and a requirement for electricity is that you have a flow of electrons. So you want to write that down. in order to have electricity, you have to have a flow of electrons. If you do not have a flow of electrons, you cannot have electricity. So you need electrons that are free to move, basically. And the idea of an electrolyte is the charges that are free to move are the ions. Because they have charges, they're free to move. This is a production of electricity, is what can result as a result, because now you have those negative charges that can move through. So what am I getting at here? You can simply just look at a compound, look at what type you have, and identify whether or not it's an electrolyte. And so ionic compounds will always be electrolytes. I'm going to give you 3 examples here of electrolytes or no electrolytes. First, we're going to look at ethanol, which you have no idea most likely what that is, except for in context, maybe you've seen it for gasoline, like you've seen ethanol in gasoline when you go to the pump. I'm going to give you, it is. And when we do our final study, which is not a difficult unit for us, I try to end the year with the easiest unit for us, but we're going to study these types of compounds. They're called organic compounds. Ethanol has this structure. It's C2H5OH. I'm going to write it out for you. So it's carbon, hydrogen, and oxygen. And specifically, it's organized like this. And I know this is going to make you be like, that looks difficult. But once I explain next unit how to get this, it's really not. It's the Lewis structure, which we used to do that back in the past. And we'll be going back to this thing in our final unit of study. This is ethanol. It says here, if we were to take those electrodes and put it into a solution of ethanol, it will not conduct electricity. It won't move the meter up. Why not? Can you justify? Why won't that happen? And why won't it be conductive? Because we care about the why. What do you need to have the flow of electricity? A transfer of electrons. Something with a positive charge? Something with a
Negative charge.
And what do you notice about ethanol? It doesn't have a charge because it's a covalent compound. So it turns out that all covalent compounds, with one very, very notable exception I'm going to bring up shortly in this example, are going to be non-electrolytes, no conductivity. And I believe I wrote that here. Covalent compounds are non-electrolytes. Because they don't conduct electricity because they don't have charges. They don't have a transfer of electrons, like Jose Enrique said. Absolutely correct. So now you can look at any compound, and if you see it's covalent, you now know it's not going to conduct electricity. I believe I told you back in the day when we were first learning covalent and ionic compounds that was such a big topic. That if you can determine the difference between covalent and ionic compounds, it gives you a lot of information moving forward. And I was talking to Mr. Dime about it, and she's like, they need to know covalent versus ionic compounds. So, because it happens in marine science, you need that information as well. And so, well, what was a covalent compound again? Just in case you forgot. What are we looking for to note that something's covalent? Oh, but how do we know that?
Because it will be done.
But how do we know that?
You would need to make the.
How can I get that from C2H5OH?
You would need
You just need to go to the periodic table, right? If everything is a non-metal, you have a covalent compound. So non-metals, because carbon, hydrogen, and oxygen are non-metals, this does not conduct electricity. That's why. And so what is an ionic compound then? What are we looking for an ionic compound? If I give you any formula, there's got to be at least a metal there. So metal and non-metals. So just in case you forgot, you should rewrite this for yourself, because we're going to be looking at this very shortly. Now it says here, KCl has a high conductivity. Can we explain that? That's seen as a metal, right? So why does it conduct electricity really well? You'll see here in the diagram it says plus minus, plus minus, plus minus. Why? But why? When we're looking at KCl, you have to remember potassium in an ionic compound has a +1 charge. Remember that? Back in the day? And chlorine in an ionic compound, you go to group 17, what charge would it have? -1. So because of these charges, it has a high conductivity, meaning it will conduct electricity because it's an ionic compound. So what's important here is the understanding of why. So ionic compounds will always conduct electricity when placed in water, which all of our solutions will be in water, and so they'll conduct electricity. Now the last one is acetic acid. And acetic acid, we have said a little bit about acids in this class. I've taught you a little bit. And the rest of this unit, later on in this unit, I'm going to go a lot more over acids. But what do you remember, if anything, about acids? Anything at all? They're corrosive, okay. Anything about their chemical structure that you can remember? Do they always have a specific element? Hydrogen. And specifically H with a plus one charge. Specifically, in order to have an acid, at the very minimum at this point, I'm going to teach more later on in this unit, but at the very minimum, we said that acids have H plus. So even if you don't know what acetic acid is, it's the acid in vinegar. We'll be working with it later, this unit in a lab. It's this. I'm going to go ahead and write out its formula. And it says here it has a low conductivity. So it has a conductivity, but it's not as great as that of a regular ionic compound. Welcome back. It's because it's a weak acid, which we'll talk about another day. But why does it conduct electricity at all? Is because it's got H plus. So acids always conduct at least a little bit of electricity because they've got the positive and negative charges, just like an ionic compound. So this means that ionic compounds will conduct electricity and acids will conduct electricity because they've also got the plus minus charge. Anything that has a plus minus charge, it's got those ions, is going to conduct electricity. And so acids will also conduct electricity. And so the first type of question you're going to see on the next slide is to identify whether or not each of the compounds conduct electricity. And this is what you're being assessed on, is to check the compound and see, will it conduct electricity? I'm pausing a little bit to give you some time if you are finishing writing here. About 20 more seconds and then we'll continue. Good. Okay. NaCl. If I put NaCl in water, will that conduct electricity?
Yeah.
Alright, so to save myself some writing, to save you some writing, let's do electrolyte with the letter E, and let's do non-electrolyte with the letters N, E. I'm extremely inventive, but that way you don't have to write so many letters out. Big handwriting. So is NaCl an electrolyte or not?
Yeah.
It is. Why?
It's an ionic compound.
If I place it in water, I get this, and I get this. You have these two separated ions, and these ions have charges, and these charges allow for the flow of electrons. So it has to have charges in order for the flow of electrons to take place. So ionic compound is the real reason, but I want you to have that visual idea of why. H2SO4, what about that one? Yes. Why? That's all like some ions, good catch. But also because, and H plus is there, right? So it's SO4 minus 2. If I were to visualize it, it's SO4 minus 2. It's the polyatomic ion there. And then for every SO4 minus 2, you've got 2 H pluses in the solution. And so there's positive ions here and there's negative ion here. C, NO2. That one.
Any.
no charges, and you can prove that by checking your periodic table and verifying that you have two nonmetals, which means that electrons are shared, not transferred. That's the idea. So Ne. Last one, C6H12O6, good old sugar, glucose specific. Ne. Because again, non-metal. I'm gonna write Nm for non-metal. Right. Nm, Nm, three non-metals, not going to conduct electricity. So far, so good? Alright, so that was an intro to solutions, some things you need to know about solutions. Now we're gonna get to the math very shortly. I think I have one more slide just to show you something you can do now that I've taught you this information. Take a look at the nutrition facts label here. And this is a nutrition facts for Gatorade, actually, which somebody mentioned earlier is one of the main places you hear about electrolytes. And so what I want you to figure out by looking at the ingredients list, what are the electrolytes in Gatorade? When they are saying these electrolytes are going to replenish you, rehydrate you. When you exercise and you lose those nutrients, you get them back from drinking Gatorade. What specifically are they talking about? So what are the electrolytes in Gatorade? Where you'll want to look at is the ingredients. This is the ingredients list here. And if you've never read a nutrition label before, ingredients are always assorted from the thing that's most there, like the most present, to the least present. Meaning you have the most amount of the first ingredient listed and the least amount of the last ingredient listed. And so the first ingredient listed here is?
Water.
Does that make sense?
Yeah, it's liquid.
It's a liquid solution, right? Everything's dissolved in water. Water is the solvent. Water is the first ingredient. That's why. Oh, look at your beverages. Look at for the first ingredient from now on. You're gonna see it's gonna say water is the first thing because everything's dissolved in water. You say you don't drink water, maybe you don't drink pure water, but you all drink water. All right, so is water an electrolyte itself? Yes or no? Is it?
Everybody's liquid. I think.
Is water itself
Oh,
an electrolyte? It's covalent. Yes? Sugar. Sugar and electrolytes. So no. Dextrose is also sugar. No. Even though you may not know the chemical structure for citric acid, you know enough to determine whether or not it's an electrolyte or not. Is it an electrolyte? Yes, because acids have H+. Right? So we know that the first electrolyte that they're talking about here is called citric acid. Well, so far, wait, what's citric acid? Do you know where you get that from?
Citrus, like oranges.
Citrus fruit, like, oranges, lemons. So you could replenish your electrolytes by having an orange. So far, so good. Okay, so we know that's an electrolyte. Is salt an electrolyte?
Yes.
I called it by its common name. Salt is the common name, but that's NaCl. That's definitely when they're referencing salt, they're talking specifically about NaCl. Sodium citrate. Figure out if that's an electrolyte. You again have never heard of citrate, but you have enough context to figure it out from what we've learned. Sodium is a metal, and the ATE ending, what does that mean? Okay. It means you have a polyatomic ions, electrolytes. Sodium citrate is an electrolyte here. The next one is really weird. I always think this naming strategy that they do on labels is strange, but I'll explain why they call it this way. It'll make sense when you see it. Monopotassium phosphate. First of all, can we answer whether or not that's an electrolyte?
That is.
definitely. It's got the polyatomic ion, it's got potassium, which is a metal. So in terms of answering my question, that's an electrolyte. What is monopotassium phosphate? You have enough context to figure it out. Mono means one. One potassium with a phosphate. That's what that reads. So what is that? Well, potassium is +1, phosphate is -3. They're telling you this specifically has to be 1. So the actual thing that's in here is KPO4 -2. Like that. That's monopotassium phosphate. And that is an electrolyte. Gum arabic, no idea, right? Probably not, because gum. Glycerol ester of roast. What is that? Probably not. We don't have enough context to figure that one out. Natural flavor. I don't think we have enough context to figure that one out. And then yellow 5. You can look up what that is. Yellow 5. Those are like food coloring. Like, you know, whenever they say yellow 5, red 40, blue 7, those are all like they took food coloring and added it to your food, and that's how it got that color. So this is like this is the lemon lime Gatorade, I believe, this specific one. And the ingredients list is slightly different per Gatorade that you have, like the different flavors, the different colors. But literally, they developed this in University of Florida, right? So that's where it got the name Gatorade, and that's because it was developed there. And so they basically just made a concoction in their labs of what can we add together to make this product. So this was made with chemistry.
So I just thought that.
Yes.
And then the scientists went, oh wait, we can sell this for money.
Well, that's, usually a lot of people's end goal is profits. So, and then they developed their marketing around electrolytes, which a lot of these electrolytes find from natural things like fruits. Anyways, what are the actual ions that are helping, before we get to the math part, what are the actual ions in Gatorade that they're talking about that are helping with our sodium-potassium pump, which I'm already giving it away? Sodium, right? In the sodium chloride, then I just take salt. And potassium. So, yes. Go ahead. And so one of the things you learn with time is that the more you look into things, you're like, oh, well, there are other options. You don't have to have this specific product for that. You could choose a different option. But this is a product that provides those micronutrients, we call them. So anyways, I figured this would be a good little deep dive into what electrolytes are and what you could actually look at when you get home, and you can find your electrolytes actually in whatever you are purchasing, eating, drinking, so on and so forth. The next thing I want to bring up here is I want you to look at this part of the nutrition facts label. Notice the amount of sodium and the amount of potassium. First of all, they put salt in this drink. Has any of you ever drank Gatorade before? Does it taste like salt? No.
No.
Why not? Oh. Take a look at these amounts. They tell you there's 270 milligrams of salt. mg is milligrams. They tell you there's 75 milligrams of potassium. There's 34 grams of sugar. Do you see the unit change? What if we were to compare all in the same unit? Back to King Henry diet and usually drinking chocolate milk. Move this over. This is 0.27 grams of sodium, 0.075 grams of potassium, and 34 grams of sugar. Do you now see how much more sugar is in there than salt? A lot. Over 100 times the amount of sugar than is salt. Why is the sugar there? Yes, to provide energy. Also to take away the bitter flavor of the salt. So they have to overpower it with sugar. Which is not great for anybody who's diabetic, by the way. If you're diabetic, don't drink Gatorade. Don't drink Gatorade. All right, so we're going to go ahead and continue, but I thought this was an interesting deep dive. I may have told you, I'm sure I told you at the beginning of the year, my initial major was nutrition. So what I was personally interested in studying was nutritional facts, labels, and figuring out what to eat that's better for you. All right, let's continue. Concentration. So this is where the math begins. I know you're so excited to get back to the math. We have two things to do today. We need to figure out how to calculate molarity and how to calculate for dilutions. And so let's start with molarity. Concentration, this term, refers to how much solute you have, so you're going to want to underline that, in an amount of solvent. So when we talk about how concentrated something is, a concentrated solution is one that has a large amount of solute, whereas a dilute solution is one that has a small amount of solute. And so it's basically the amount of sugar that I initially put in here was small. I just put a couple of things. If I want to make this more concentrated, what do I got to do?
Add more sugar. That's so much sugar.
If they're diabetic, without their insulin.
Take a sip.
Sugar's crazy. You know why sugar's crazy? I just put a ton of sugar in it. Like a ton of sugar.
How much sugar would it take for all that to just become sugar?
It looks clear again.
Yeah.
You can't tell. Still looks clear. I could add more sugar and it still will dissolve.
Give a
Sugar
glass
is
of water to
wild.
my body.
Sugar's wild like that. So anyways, a concentrated solution basically means you have a lot of solute in comparison to a dilute solution, which means you have a small amount of solute. And this matters for your chemistry and you, yes. You have things like blood glucose levels. And if you're ever going to be a doctor or you're going to be someone who's going to go into medicine, you get chemistry readouts actually for people, and it'll tell you how much they have of different nutrients in their body. And it'll give you levels and say whether they're in the right range or whether they're outside of the correct range. And if they're outside of the correct range in their blood chemistry, you know something's wrong with them medically. They have some kind of health problem, and we'll have to investigate and figure out what happened. Also, if you want to be a veterinarian, you do the same thing, but with animals, actually. You have to get their blood test readings, and you see, and it also does this with urine tests, and it gives you a printout of what their different levels of different nutrients and different things like bacteria levels in their body, and it'll tell you like what to do from there. So it's all chemistry and concentration. This is a big area of study, which is why we have to study it in the foundation class. For Cambridge, we're only going to study one unit of concentration. That's good news for you because there's many others. There's like 5 or 6 units of concentration. But for the purposes of Cambridge International, they always do 1 unit for concentration. That way you compare everything the same across the board. And that unit is called molarity. Oh. Moles. Man, we got to return to that. So the unit of concentration that Cambridge exclusively uses is called molarity. And so Cambridge's unit of concentration is called molarity. That is the value, the numerical value we're going to use to compare dilute versus concentrated solutions. And I know you're going to be so happy about this. The abbreviation for molarity is capital M. Like N? Do we use M for anything else in this class?
Yeah.
No, we never use M for moles. We use MOL for moles, if you'll recall. Because we use M for molarity. But what else do we use M for? Yeah, right? Lowercase m is meters. MM, lowercase. This is M is meters, right? MM is millimeters. I'm teaching you right now that capital M is molarity. And what's MM?
Megamole.
Molar mass. That's where the fact is crazy, where you see the letter M in like 4 different places and it means different things. So if you see one capital M from now on in this unit, That means molarity. What you're being asked for, what you're being given is molarity. That is what it means. And so what is molarity? Well, there's a formula for it. I know you're very excited. Formula means math. The good news is Cambridge only uses this unit of concentration. The bad news, I guess, for you is that it's something you must memorize. You got to memorize this formula. To calculate molarity, it is the amount of moles of solute you have divided by the liters of solution. We also call it molar concentration. So let's get to the math. And that's going to be where we're going to be for the rest of the class period today. And we do have to get through it because remember, like I said, we don't really have class on Thursday, so we got to try to get through everything today. This is a future you look at the lab you're going to be doing on Monday, which is preparing a solution. It's going to look very much like you're making potion because that's what the bottle looks like. It is called a volumetric flask, and you're going to be preparing a solution of a known concentration. We'll be doing that on Monday of next week. Today, we're getting through the math that you have to understand for calculating concentration. We'll get to the exercise part on Monday. Calculating molarity. So how do we do this? Welcome back. How do we do this? Well, let's take a look at the question. And just like solving any other math question, we're going to go through our process. This first question talks about IV. Anybody ever heard of an IV before?
Roman numerals.
Someone's in a hospital. And yes. Nutrients.
Oh,
You
like they
put a
put the
IV,
nutrients, they
right?
plug it in.
It's basically a bag. And that bag contains salt and sugar. Actually, the salt for the electrolytes and sugar for nutrients. And so those nutrients have to be specific concentrations. And if the person who's preparing it gets it wrong or changes the concentration, you can, at very minimum, have a medical emergency for that patient. And at maximum, it can kill someone if the IV is prepared incorrectly. Which is why if you are planning to go into the medical field, become a nurse, you have to study chemistry, actually. You do have to study chemistry for that field because you have to understand these ideas and you have to, get those concentrations right. And there are medical malpractice lawsuits that happen if things are done improperly. And so that's why this question is talking about IV. So IV solutions are often administered to patients in the hospital. They're telling you that a saline solution, which is salt, by the way, saline, is 0.9 grams of NaCl in exactly 100 milliliters of solution. That's how much grams have been placed in that amount of solution. What is similarity? So how will we answer the question? What are our steps for solving questions? And I made sure I wanted to write them out properly. What is the first thing we should do when we're solving a question? What is given, right? So what is given? What is asked for? What is asked for? What's given is grams of solute, right? NaCl is a solute. And what is this? Milliliters of what?
The solution.
And what is asked for? The molarity. That's the first thing, is identifying, like annotating your question. What am I being given? What am I being asked for? If you don't start here, and this is where a lot of people go wrong. You want to just skip to solve every question without thinking about it first. If you don't think about what is the formula I need to use, you may get very confused in these questions because there'll be more than one formula you could use. Right now we're only doing one though. Second step. What's the formula needed? Solute over liters of solution. And then that's the formula. And that's the one you have to memorize to calculate molarity. Next. You have to check your units. Do your units match? Are your units correct? So that's what we're here. Check units of your given. And if they're not the right ones, what do you have to do? If not correct, you have to change them. Wait, what do you mean? I have grams and it says I have to have moles? Do we know how to do that?
Yeah.
We did that. We did do that. This is what we spent a lot of time on last unit. So you're gonna have to change the units to the correct ones. So let's do that now. 0.9 grams NaCl, how do we change that to moles? 0.9 gram NaCl over 1, change it to moles.
And the bottom will be
It's
that
gonna be 58.5 grams on the bottom, which is the molar mass. And on the top, it's gonna be 1 mole. You have to divide the two. You have to divide by the molar mass. This is why I had you practice in the lower today to remember that this is the thing that you did, change grams to moles. So you're gonna do 0.9 divided by 58.5, and you should get 0.015 moles of NaCl. Is that molarity? What else do I gotta get? You need to also find out. So that's my moles of solute. Got that. What's the other part that I need for this calculation? I need my moles of solute and I need my liters of solution. What do we do for that?
So grams?
King Henry died unusually drinking chocolate milk. If I've got 100 milliliters, how do I change that to liters? Millis here. Where's liters? The base unit, right? You have to move your decimal over. 1, 2, 3, 4. 3 plus that. That's why I taught you a trick, so you can do this quickly. You don't have to write it out every time. You just know to move it back. If you have it in your head. Henry died unusually. Where is right now? 0.100 liters is the correct unit. So I've checked my units. If they're not correct, I've changed them. So now what do I do? Well, finally, plug in the formula, right? Plug in the formula. Plug into formula. So now we're going to use our molarity formula. Molarity equals how many moles on the top? 0.015 moles on the top. And what's the volume for the bottom? 0.1. And our final answer will then be 0.15 and capital M NaCl. So that's how you calculate molarity. Notice conversions are here. You're going to have to, it's going to be assumed that you know how to do conversions, because that's one of the steps. I'm giving you a little bit of time. We're going to take a look at the next question. The next couple of questions aren't too crazy because they will not require so many unit changes. So we're going to go over the next one shortly. Yes. Go ahead. Somebody's out right now. Or Damien, did you return the pass? Hmm? Okay. Yes, Mary Jo. Continue. All right, next question won't look so involved. The involving parties have to change the unit. Let's try this next one. Oh, now we're talking about bleach. Bleach, don't drink it. Is a dilute aqueous solution of sodium hypochlorite, which is specifically NaCl. How many moles of solute are present in 1.3 liters of 0.45 molarity NaCl? Underlining my given. I'm underlining what I'm looking for. Notice that you're always given two things here. And this is because the molarity formula has 3 components. Our formula to solve molarity questions is N equals moles over liters. Notice this time, I did not write solute and solution because I'm trying to save writing. But it is solute on the top and solution on the bottom. You can write it just like this and memorize it like this because as long as you understand how the units change, this is the least amount of writing that you have to do. Capital M equals mole over liter. So now, we know what we have, we know our formula. What's the next thing we do? Check the units first. Are the units right? You may have already done this in your head. Liters, that's correct, right?
Yeah.
Capital M, that's correct. That fits in right there. So if your units are correct, what do?
You just
Plug in the value. So units are correct. I'm just going to put units check mark just to remember that you do have to do that to check them. And then plug into formula. And here's the math. So where I see M, I'm going to put 0.45 because that is the molarity. I'm looking for moles. So you can either write MOL because you're searching for that, or if you really like algebra, you could just call it X. It's the X you're looking for, right? And then the liters on the bottom is 1 point. How do we solve this for moles? 0.45 equals mole over 1 point. I'm solving for moles, right? If I'm solving for moles, I have to isolate it. It has to be private. This is algebra. This is actually algebra. And so in order to solve for moles, because moles is being divided by 1.3, what do you have to do? Inverse operation of a division, which is a multiplication. You would multiply both sides of the equation by. Some people say just by 1.3, or you can say multiply by their reciprocal, which is 1.3 over 1. Multiply both sides by 1.3, cancel out 1.3, and what's your answer? I get liters, or sorry, I get moles is 0.59. Check to see if you get the same thing. The two significant figures. .59. Check in your calculator to see that you got the same. Which is just the multiplication of 1.3 and 1.45. We have one more scenario to look at with calculating regular molarity questions. And then we're going to look at dilutions before we go. Continue. Okay. So, volume. And you can see all I'm doing in these different examples is calculating for different things with the formula. So now you've got bleach. You've got 0.5 moles of a stronger concentration solution, 4.34 molarity. And they're asking you how much volume in bleach in milliliters do you have. So underline your given numbers. Moles, molarity. What are you being asked for? Volume, right? After you have underlined what's important in this question, you should then go to your formula. Your formula here is capital M equal mole over liter. Is molarity the correct unit to go in the formula? Capital M. Can I just plug 4.34 in right there? Yes. Is 0.5 moles, is that the correct unit for the formula? Yes. So the units are good for the formula, so you can plug them in. So you've got 4.34 equals 0.5 over L. Now your algebra skills come into play. How do you solve it?
Yeah.
There's a couple of ways you can reason. The traditional algebraic way is, well, liters is on the denominator. You cannot solve for a variable as long as it's in the denominator. You have to get it out of the denominator first. So you multiply both sides by L to get it out of the denominator, like that, right? And so you get 4.34 times L equals 0.5. Now, how do you solve for liters now? Subtract. This is a multiplication. What is the opposite of a multiplication?
Division.
Division. 4.34. 4.34. And so your liters here is 0.5 divided by 4.34. You have to be able to put the calculator correct, and you will get 0.115 as your liter of solution. Final answer. That's the volume, but it's in a very specific unit in this formula. What's the unit? Liters. This is liters. That's capital L, right? What is the question? You will have to change the liters to milliliters. So how do you do that? This way. And so your milliliters is 150. Again, that's utilizing the King Henry diet unusually drinking chocolate milk strategy of just moving the decimals to left and to the right. All right, so questions can be easier or more difficult depending on how many conversions you have to do. We have one more topic to cover. So I'm going to skip the question for this class that says your turn and go to the last topic. And then if we have time at the end, we'll come back to it. But I want to make sure that you have what you need to practice before we do the lab on Monday. So we're going to do the last topic for the day. So we're skipping this for now. If we have time at the end, we'll do it at the end of class. So let's get to the last topic. So the last topic today is called dilution. And the process of dilution is one you may or may not be familiar with. Has anybody ever heard of dilution before? What is it? So it makes less concentrated, okay. Making less concentrated, but how? So you know we have like a lot of sugar in here, right? How could I make this less concentrated? Oh, so the process of dilution is adding water. So making less concentrated by adding water. That's really what a dilution is. The dilution process to change concentrations. You're going to use that if you study AICE chemistry. That is one of the processes in paper 3 that we'll need to do is we need to do dilution. And if you study AICE biology, actually in AICE biology, one of their paper 3 exercises is a serial dilution, which is basically add water to get different concentrations. Same idea. And so we do have to understand this topic. I'm going to go ahead and just show you with a very simple demonstration what this can look like. So I have about 5 milliliters. Yes. I have 5 milliliters of food coloring and water. Nothing dangerous. That's why I have the gloves. And I have 500 more milliliters of water down here. So what do you think will happen to the food coloring solution if I put it into this 500 milliliters of water? Will the color stay exactly the same? Let's see. Now let's compare to what I had before.
Clear. Pink. Pink.
Why? But there is as much dye, isn't there? We didn't change the amount of dye. Compared to the water, meaning as we put more water in, it pushes the solute particles farther apart from each other. And so the color is not as intense. It's not as deep. The concentration is less. So adding water the concept here to understand is that adding water always decreases the concentration. So adding water, so increasing the volume by adding water will do what to the molarity? Will always lower the molarity. So you're going to want to write that down. Increasing the volume will always lower the concentration. And you can see that in practice just by looking at the differences in color like I did in this little example here. And you'll be doing that in your lab. But the amount of solute is exactly the same in both. You're not changing the amount of solute. You're changing the amount of solvent in this process. So this leads us to our final formula for the day. It is called the dilution of solutions formula. And it is M1V1 equals M2V2. So this is your second formula, and this also does need to be memorized. This is the formula that you use when you add water to a solution to change its concentration. That's what it's called, the dilution of solutions formula. What you're going to notice is difference between this formula and the one that you had before for molarity is in this you've got two volumes or you have two concentrations. So in all questions with dilutions, you will either have two concentrations given or two volumes given. And that's the way you're going to know that you're using this formula and not the traditional molarity formula that I taught you. So you'll want to write that in before we continue. The other thing I want to make note of before we move on is this side right here is your initial molarity and volume, and this side right here is your final molarity and volume. So M1 is the initial concentration, V1 is the initial volume before you add water, M2 is your final concentration after adding water, and V2 is your final concentration, or your final volume after adding water. So that's what that stands for. We're going to use that for some questions. This is our final math question for the day. I'm giving you a little bit of time. You'll see on the next slide when we get there. By the way, you should be writing full notes. I will be checking these. Your final note check will be with the last unit, and all of your notes will need to be complete in order for you to get that note check score. All right, so let's go ahead and get to it. On this slide that you see here, this is actually going to be similar to the lab you're going to do. It's going to give you a preview of the lab you're going to be doing on Monday. You'll be taking a solution and you'll be diluting it to a different concentration. And you'll see here that there's this interesting piece of equipment. There's that bulb at the top. You're not going to have it look exactly like that. You get something a little bit more refined, actually. But you will be using, it's called a pipette gun, actually, in order to figure out how much you exactly need to transfer. And I'll be explaining that to you before the lab, of course, exactly what you'll be doing. But this is the technique. And the lab you'll be doing on Monday is about technique, really. It's figuring out the technique of how to properly make a concentrated solution of a specific concentration as requested, and then how to dilute it to different concentrations afterwards. That's the technique we'll be doing for our first lab of this unit. Today, again, we're focusing on the theory, which is really just the math here. How do we solve questions that are with dilutions? This is our last set of questions we're going to do now. So first question, practice one. How many milliliters of aqueous 2 molarity MgSO4 solution must be diluted with water to prepare 100 milliliters of aqueous 0.4 molarity MgSO4? So breathe in, breathe out. How do we know this is a dilution formula question and not a molarity formula question? So you got keyword to tell you which formula you're using. There's another way you can figure it out if that keyword doesn't show up. So I know that my formula is gonna be M1 V1 equals M2 V2, right? And know that that's my formula. What is the other way I could figure it out if I didn't get it from reading comprehension? Look at the numbers. Underline them or circle them. You've got 2 molarity MgSO4. You've got 100 milliliters of is a linking word, 0.4 molarity MgSO4. You have 2 different concentrations, meaning you're taking a more concentrated solution and you're making it less concentrated. That's the process. So if 2 concentrations are given to you, or 2 volumes are given to you, that tells you you're definitely using the formula. Once I know I have to use the formula, now I have to figure out what goes where. That's the important part. And so I want to bring up here, capital M stands for molarity. What does V stand for? It's interesting. I wrote V. I didn't write a unit. Did you notice that? I didn't write whether it's liters or milliliters. Why didn't I do that? And it's not written like that. Most people nutritional won't write it as liters or milliliters. As long as the units match, you can use whatever unit of volume you want in this formula. That's what's really cool about it. You can use whatever unit, any unit of volume, because they'll always cancel properly due to the nature of the way the equation works. So you can use any unit of volume here. That's great news, because you've got milliliters and you want milliliters. Those units match, so that means you're just going to be able to plug in the numbers you're given. So what goes where? Remember, this is your initial, and this is your final. And the process of dilution is to make a more concentrated solution into a less concentrated solution. What does that actually mean? The value of your first molarity should always be greater than the value of your second molarity. So if you've got 2 molarities given to you, you should know which one goes where. And if you were given 2 volumes, which one should be bigger, the first or the second? V1 should always be less than V2 because the processes you're adding are water, right? So you can use this to help figure out what goes where. So we've got 2 concentrations. Which goes on which side? Does 2 go on the left side or does 2 go on the right side? Compare the numbers 2 and 0.4. 2 goes on the left side because that's more concentrated. And 0.4 goes on the right side. So we've got that. We've got 2 out of 3 parts that we need to figure out. Now the other thing we got to figure out here is, well, where does the 100 milliliters go? Does that go with the 2 or does that go with the 0.4? Can you figure that one out? Where? And the key here is to recognize it's 100 of that. The of is the linking word between the 2. That's why you saw them annotated this way. These 2 are linked together, so they have to be on the same side. So 0.4 will go with 100. And that means that what we get here will be V1. We're solving for V1. For any algebraic equation, you have to have only one variable. And everything else you must have the information for, or else you're not going to be able to. So we're solving for V1 here. So then we do it. Do the math. 0.4 times 100 is 40 in algebra. And then how do we solve for V1 here? Do what? Divide by 2. And you get V1 equals 9. Unit is what? What is the unit of volume? If we start with milliliters, we end in milliliters. The only thing you got to remember about volume is they got to match. So this is milliliters. We'll do one more before we go, of course. Homework. It is digital today. It is on Science Geek. It's 2 sets. One is on molarity and the other one is on dilution. And it's going to be due Thursday. That gives you time. You can either do it at home, or if you are not testing on Thursday, then you can do it during the class period to do the exercises for what we're learning right now. on? All right, question 2. Let's try this again. 100 milliliters of a 0.3 molarity copper sulfate solution is diluted to 500 milliliters. What is the concentration of the diluted solution? So underline your key important things: volume, concentration, volume. Because I have 3 givens. 2 of them are volume. And it says the keyword dilution. What's my formula? Yeah. So once I figure out my formula, the next thing is how to figure out what goes where. My suggestion is to look at what you have 2 of. What do you have 2 of this time? Volumes or concentrations?
Volume.
Volumes. You've got 100 versus 500. You always start with a lower volume, and then when you dilute, you add more. So that means that between 100 and 500 milliliters, would that be V1 or V2? The greater volume. 2 actually, because you had to add water to get to it, right? And V1 is 100. And where does the 0.3 go is the next question. It's 100 of 0.3. So these 2 go together. So where does 0.3 go?
On the left hand.
0.3 times 100 equals. Now you've got everything. We're solving for the second concentration because we have to have 3 out of 4 things. We're solving for the 4th. And then we do the math. The math is 0.3 times 100, which I believe is 30, equals M2 times 500. Now what are you going to do? Solve for M2. Right, both divided by 500. It's got to be whatever's next to M2. 0.06 equals. We'll stop here. We'll do the last practice question before we do the lab on Monday. So bring back your notes on Monday. We'll do that last practice question after we do the Bellers, but before we do the lab probably.